So thank you very much for having me. I am an engineer, but really a hydrologist, and so of course hydrology kind of falls sometimes under earth science, geoscience, sometimes under engineering. So I'm somewhat in between. As Karina said, my main focus is on low flows and drought resiliency. So that's what I'm going to be talking about today. And kind of taking a longer temporal perspective on drought, which hence the tree rings. So there'll be quite a bit about reconstructing flow here. But to just sort of point at why we should care, and unfortunately this might be tough to see, so I'll just have to tell you what it says. This is every year the World Economic Forum posts this document, and they bring a bunch of smart people into a room and they say, what are the most dangerous challenges for the world, society, so on. And then they put them on this grid in terms of sort of most severe impacts to least severe and low likelihood to high likelihood. So you can imagine this upper corner is the really scary things. It's the high impact things that could really affect the world and are likely to occur. Just to kind of figure out where we're standing, weapons of mass destruction, so that's sort of the low likelihood but massive impact. But the three things that I'd like to highlight here: water crises, extreme weather events, and failure of climate change mitigation or adaptation. So these are things that we think are likely to occur, but could also affect massive numbers of people. I might be preaching to the choir here, but yeah. So this is why we care about water, droughts, and water availability. So that brings us to the big question, which is how vulnerable are our water resources to an extreme drought? A seemingly simple question, but we're going to attack it in a few different ways. So the traditional way, this is a nice healthy, this is actually one of the streams that we're going to be talking about when it's running nicely. So this is northern Utah. So I'm an engineer, so I tend to approach these things from an engineering standpoint. So generally when we talk about stream flow drought, and I'll sort of zero us in on what we're looking at here, we tend to look at risk in terms of frequency. And so we'll define something like the 100-year drought event, which has a 1 in 100 or a 1% chance likelihood of occurring in any given year. Not something that occurs every 100 years. I have to say that over and over to my class, and still it happens. And the way we do that is we plot some measure of drought or low flow, in this case a 7-day, so we take a 7-day moving average, and we find the lowest 7 days in any given year, and that we plot that single point on here, and we plot it against frequency, and we can pull out, or non-exceedance frequency, we can pull out a return period. So in general, we've had good gauging data on streams in the US. We're actually very fortunate here in the US to have good gauging data that goes back something on the order of 70 to 80 years, which you can now see the problem here. We have 70 or 80 years of data, and then we are trying to estimate way out here. We're essentially extrapolating out to the 100-year frequency. And people will even say we need to be designing for the 200, 500, 1,000-year frequency drought events based on 70 years of data. And so small changes over here can make massive changes when we're extrapolating. So how can we better quantify the likelihood of these really extreme events? We could backfill in with, for instance, 400, 500 years of reconstructed droughts to give us a better baseline. And now we're no longer extrapolating out to the 100-year storm event. We have much more confidence. I should have put confidence intervals around this line, but those confidence intervals should suck down significantly by filling in all of this additional flow information. But then what's the other thing that we have to consider looking forward is that this historic baseline might not be informative. Well, it should be at least somewhat informative, but it might not represent our future climate due to climate change. And so we somehow have to link these three different data sources, and we'll talk about the challenges with doing that, to try to get a good sense of the likelihood of these really extreme events, what kind of risks these impose, and where we might be moving forward with climate change. So this is sort of my broad scale question. The problem, well, I'll get into the problem in a second. So just a little bit of background. I know there's quite a bit of ice core reconstruction that goes on here at Byrd. So for some of you, this will be super simplistic, but just one slide so that we're all on board. I do quite a bit of my work with tree rings. They're a really good proxy for water or flow because water is obviously, if you choose your trees correctly, water is a limiting factor for tree growth. And so we can look at the rings and we can relate the growth in the tree ring to water availability. So the reminder here is that the tree shouldn't be, you'd like to think that the tree would be sort of a dipstick. You want it right next to the stream. In fact, you want it in a water scarce part or a water stressed part of the watershed. So you don't want it right in the stream where it's will always be happy. You want to try to increase the interannual variability. So you choose your trees very carefully. And then we can link sort of living tree samples and through a process called cross-dating, we can link those with dead wood and we can go even further back. So for instance, this is one of the reconstructions that I'm going to be working with here by a colleague, Justin DeRose. This goes back to the year 800. So now suddenly we've increased our temporal scale from 60, 70, 80 years of data to, well, I can't do the math in my head, 1,200 years of data. So this gives us a really good baseline, but it's not without problems. So one of the problems here is an incompatibility of scale, both temporally and spatially. So as you can imagine, our stream gauges are sitting in the stream and they're taking, in some cases, hourly, daily, monthly data. Whereas up until now, our tree rings are reconstructing at an annual scale. There's also some spatial incompatibilities, and we'll talk about that later. But again, we're dealing with mixing historical proxies with actual observations or reanalysis data, and then mixing in climate model data. There's potential incompatibilities here. So I'm going to focus on this temporal incompatibility because we need to try, if we're going to link this to water resources risk, we need to dig down beyond the annual because water decisions aren't made at an annual scale. We need to at least be at a monthly scale in order to do this. So then the question becomes, can we create a monthly reconstruction out of annual tree rings? And that's been a major focus of my research. So just to orient ourselves, this is the reconstruction, the annual reconstruction that I was focusing on. It's in the Bear River, which is the largest tributary to the Great Salt Lake in northern Utah. It has this really unique path. It starts very near to where it empties into the Great Salt Lake, but it meanders out of Utah into Wyoming, back into Utah, back into Wyoming, into Idaho, back into Utah, up and over the mountains, and into the Great Salt Lake. So you can imagine this is just a prime place for water fights. And so people are really concerned about how to manage for large-scale droughts in this part of the world. So we have this existing annual reconstruction that was created in 2015, and the question is, can we get into a monthly scale? So there are a few different approaches that we could take to do this, starting from the absolute simplest. You don't know anything about hydrology, let's try, it's essentially a null model, which would be, let's take all of our observations and let's divide each of our months by the annual reconstruction, and then create some average pattern. And so you could imagine each month would get applied some monthly fraction to the annual reconstruction. So if, for instance, the median fraction was 22% over the summer of the annual flow, then you take your annual reconstruction, you apply 22% to that, and you get some kind of monthly reconstruction. This obviously takes into account very little hydrologically, and it produces some weird artifacts. So the first off, you guys probably would pick up on this very quickly. The shape of each one of these each year, the monthly shape looks exactly the same. It's just scaled up or scaled down. And that's not the way that watersheds actually respond to flow. So for instance, here's the blue line, which is our annual reconstruction. The black line is the observed, and the red is our monthly reconstruction using this really simple model. So you can see each one of these years looks exactly like this, has the exact same shape, just scaled up or scaled down. So there's problems with this. We're already somewhat of the way there, but it's not functioning correctly. So what could we do better? Well, this is very similar to a lot of statistical downscaling methods where we normalize both the annual percentile and each month within the year, and then we assume if the annual flow is in the 20th percentile, then each month within that year is in the 20th percentile, and we back calculate a flow. So that's a reasonable assumption again, and does pretty well. It gives us a slightly better shape. It hits some of the peaks a little bit better, but it's creating an artifact here, which is that because our reconstruction is based on what's called a water year, when we transition from, for instance, an annual percentile that's in the 20th percentile into a wet year, for instance, the 80th percentile, we have this sudden jump, this red line here. Basically, our peak flow is working backwards in our reconstruction. Again, that doesn't make sense. So we need to do a little bit better. And so the final way to actually get at this question is to use a more of a regression approach. And so instead of estimating the flows directly, we can estimate a monthly normalized flow, the percentile. And we can use a few different types of, or we can consider a few different types of predictors. Things like not just the year in which the month occurred, but the previous year's percentile. And just for validation, the year following, which it should never involve, but we tested against that. There are also some reconstructed climate indices. So there are reconstructions of, for instance, El Nino, which we thought might have some value here, where the trees aren't growing during the winter. Maybe El Nino predicts winter flows better than the tree rings would. So we considered those as well. And finally, this doesn't tell you a whole lot of information, but looking at regional tree rings, we can use principal component analysis and pull out differences between different species, different elevations, different regional patterns, and link all of these together to try to estimate our monthly percentile and then get to flow. And by doing this, now we're doing a pretty good job throughout the year. So we've gone from this blue line, which has relatively little information, to this red line, which really picks up the monthly pattern of flow. Obviously, there are better ways of confirming that. So we can measure something like the Nash-Sutcliffe efficiency, which is really common within hydrology. It's called something else, and now I'm blanking on the name, but essentially a 0 here would mean that the null model would be just as good as the model that you're suggesting, and a 1 would mean that you would have a perfect fit. So here, the blue line is our monthly fraction model, that really simple model. These are our October through September months. And as we increase our predictors and our complexity of the model, you can see we were always doing really poorly during the fall. And there was a huge jump up to this red line once we allowed the previous year to enter the model. That makes sense physically. And then as we add a few additional predictors, we start doing a little bit better even through the summer. So we still struggle in the spring. That makes sense because it's actually more tied to temperature because this is a snow melt driven catchment. So is the snow melting, is it not? But overall, we're doing pretty well. And the results make sense. This is just graphically showing the coefficients from the previous year. So it affects October through the winter until the concurrent year picks up in this orange line and runs through the summer. Again, makes sense. And fortunately, this blue line, which is the year following, stays near 0. If that was a big spike, we'd have a problem. And this is just me showing that we also looked at some regional things, different species, high elevation versus low elevation, which matters here if we're talking about snowmelt. But I won't dig too far into that for time. Okay, so now we potentially have this monthly reconstruction of flow. What do we do with it? It's this massive set of data. How do we actually parse out whether drought is getting worse or not as bad, or how much risk we have? So whenever you say vulnerable, you really mean risk. So let's apply this to a water systems model and see what kind of risk we might be looking at. So this is the actual systems model for the Weber River Basin. So just to orient you, here's the eastern part of the Great Salt Lake. Here's Salt Lake City. And the Weber Basin, this Weber City is sort of big suburban complex north of Salt Lake City. And they pull water from all of these mountainous catchments. They have several different reservoirs, and ultimately it makes its way. So there's very little population up here, but that's where all the snow and water is. And then they route it down here. And they're projecting massive increases in population here. So they're very concerned about their water availability. More so than normal, and they care about water a lot normally. Massive. I've been at some interesting fights with the Water Commission. So, okay, so let's look at this, look at our monthly time series, our reconstruction, and try to pull out some drought events. So here we have almost 600 years of reconstructive flow. And if we make some definition, so if we define a drought event, as any time that flows below 50th percentile, so it's drier than normal, for at least 3 months in a row. And we allow some gap filling, so we don't want it to be really noisy. So if 1 or 2 months just eke up above 50th percentile, it's still the same event. So that's how we define our drought events, and we get about 140 total events over this time period. Then you can pull out a bunch of different drought characteristics, but in this case I'm just going to be focusing on a measure of severity, which is the minimum flow percentile, and a measure of duration, basically how long the event occurred. And so you can plot those two dimensions just like this, where we have, again, severity, so the lowest percentile, starting at 50th percentile, which is where we started to define a drought, obviously going down to 0, and duration. Not surprisingly, here's the Dust Bowl drought, the 1930s, which always shows up in the western US, actually in most places in the US, as the drought of record. And then there are a few other events. The early 2000s, late 90s were a particularly dry time period for this area. Okay, but again, this gives us our observations. The nice thing is now we can increase our data and add in all of our reconstructed drought events. The thing that I didn't mention is, and I wasn't responsible for the climate change part of this, but we also have climate change projections for flow on this river. So we can also add in some climate change scenarios and compare those relatively to our reconstructions and our observations. We can get into what these climate change scenarios are later. Well, I shouldn't draw attention to it, but we can talk later. But the other thing that I was really interested in is so this is still a massive amount of data, so we still need to sort of simplify it. So can we talk about drought types? And so, using those 14 characteristics of each one of these droughts, we can do some clustering and try to come up with some really broad drought types. And in doing so, there's about 9 or 10 of these, but basically all of these ones in purple really don't matter because they're less than a year. So if we're talking about real drought types for this region, we come up with about 4 that we might be concerned with. These orange ones, long duration, more than about 3 years in duration. Sort of these middle range, these blues, about 2 to 4 years. And then these greens, which were relatively not too severe, and these reds, which are just sort of this subset. Why am I doing all of this? Well, because the water managers are really concerned about which one of these classes might be a problem in the future, and are we going to push more into these? And I will come back to those clusters in a second, just to say that we can also run this entire time series through our water supply model. So this is a simulation of the total reservoir storage for the system using these monthly flows, linking reconstructed observations and one of our climate change scenarios. And the managers have set 3 different trigger levels of where they start going into water restrictions, progressively worse and worse, obviously. And so we could look and say, this mid-1600s drought actually looks significantly worse than even our drought of record, the 1930s. But it actually looks not that different from some of our climate change scenarios. And these climate change scenarios are basically a delta index version of the last 30 years. So we've shifted from basically this part of the time series to this. So this got some of the water managers significantly concerned. You can look at the frequency, so the proportion of months in each of these. So not that surprisingly, our reconstruction and our observation, even though our worst event was in the mid-1600s, our reconstructions aren't that different from the last century. But we're going from, in water restrictions, something on the order of 2 to 3% of months to something closer to 10, 15, 20 in our worst case climate scenarios, which obviously is problematic. And the reason I showed these clusters is that all of those failures occurred in this gray region, and they were almost always these red clusters. So this is the minimum storage for each one of the events. So now we can tell the water managers, these are the types of droughts that you need to simulate through your system. And if you want to come up with an adaptation strategy, these are the ones you need to be concerned with. And the last thing is that we also created this website so the water managers, you also can come in and actually play with it. So it's paleofluorg.org. So often these reconstructions are in CSV files, they're hidden, they're tough to actually get at. And this is a tool where you can actually interact with this massive data, so you can zoom in on the time series, you can drag it. You can also calculate extremes, so you can set a threshold and you can say, how often am I below X CFS? And there's about 100 or so reconstructions in this website. They're pulling from NOAA, obviously with all of the citation data and so on. So it's just an easy way to visualize all of this data. Yeah, I'll stop this because I don't want to run way over. Well, I'll show the extremes here. So it'll plot the distribution. You can change your threshold here, and it'll tell you there were 1,200 exceedances of this flow. You can pick out a month, you know. So I welcome you to check that out. And I'm just going to end with sort of my view of what the next steps are. So to come back to this table, which is roughly where I started. So I was looking at this question, the temporal incompatibility. Can we do better with our historical reconstructions to make it align better with our observations? So in this case, I've shown that it can work for 2 or 3 watersheds in northern Utah. The question is that expandable to other areas? The other issue is that our reconstructions are relatively limited in terms of coverage, or at least the ones that we have access to at the moment. So there are a lot in the western US. In terms of good flow reconstructions, there's a really good one on the Potomac River, but beyond that, we're starting to move into more temperate regions, but we need more of those. And finally, there's just some assumptions that are going on here. We're removing some of our long persistence in our tree ring signal, which can cause biases in trying to link reconstructions with observations. Likewise, as we're working backwards from our climate change models, there's also some persistence issues with those as well, but potentially different persistence issues. So that's a question that needs to be answered as well. So just quickly, so where I think these sub-annual reconstructions are moving, we need better hydrology. So already trying to pull off, for instance, the base flow out of the quick response has been an approach that I'm working with Max, who's a postdoc who'll be here starting in the spring. It's already the spring, in the fall. So this is correlation looking at just base flow on the Potomac River. And you can see that a lot of these chronologies are doing really well for predicting Potomac River flow, except for in the spring. So basically, this is early work saying we might be able to do this in a more temperate climate not just a snowmelt-driven Western US kind of climate. Can we get other places? For instance, the Potomac River, we've got good chronologies in Ireland and England. So if you're talking really wet, let's see if we can do it there. Other places in the world. And finally, this is just that temporal resolution. So this is some work that I'm doing with a potential student. She was really excited about the fact that if you do some time series decomposition on these, that our reconstruction is actually reconstructing what is essentially the same low frequency pattern as our observations. That's great, but it's not doing a great job. It's not as continuous through the sort of lower frequency or the higher frequency. So more questions there. And finally, actually doing some field work and trying to link these processes to measurements. So this is Gil Bohr, who's in my department, runs this eddy covariance and has these stem water sensors. And the question is, can we validate these tree rings as actual measurements of flow from a physiological standpoint rather than just from a statistical standpoint? With that, I just wanted to thank, so a lot of this work was done as a combination here of Ohio State and Utah State. Weber Basin was very kind to let me show some of the work that we're doing for them. And all of these tree rings were, so I didn't collect any of them, so the Wasatch Basin was really responsible for doing all the field work there. And with that, thank you very much.